we go. So, this is just more of what you saw yesterday on the board, but here's the video.
Ernest Rutherford was one of the first to show that radioactivity could consist of 3 distinct types of radiation. The 3 types differ in their response to an electric field. A source of radioactivity is passed through a hole to form a beam. The beam is directed at a fluorescent screen, which is illuminated when it is struck. In the absence of an electric field, all the radioactivity beam strikes the target at a single point. When an electric field is applied, the initial beam is separated into 3 components. One of these is deflected upward by the electric field, indicating that it is negatively charged. These radioactive emissions are called beta rays. A part of the beam is deflected downward, indicating that these particles are positively charged. These radioactive emissions are called alpha rays. Notice that the alpha particles are deflected less than the beta particles by the same electric field. This occurs because the alpha particles are more massive, but the amount of deflection is also determined by the relative energies of the different types of radiation. The portion of the original beam that is undeflected is due to radiation that is not charged. These emissions are referred to as gamma rays.
Okay, so I found it funny because that thing, little spiel where she was like, yeah, the alpha due to the different energy and the blah, 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 makes no sense to anybody. I mean, I kind of have a concept because I'm a chemistry teacher, but it's confusing to you, I would think, maybe not. Basically, what do you need to kind of understand? Alpha doesn't deflect as much because it's bigger, has more charge, and it's bigger, it's heavier. So it just does, the field isn't strong enough to pull it down as far as beta's getting pulled up. That's all. Gamma goes straight through because it doesn't have a charge. Beta is negative, so it's attracted to positive. Alpha is positive, attracted to negative. If there was a positron stream, where would it go? If there was a positron, would it go straight through, would it go up, or would it go down? Down, right? Because positron would be attracted to the negative, right? So, and then the next thing, she just shows each particle, and she just says gamma is kind of like an X-ray. And it is kind of like an X-ray, all right? Which of those 3 is the greatest, has the greatest penetrating power? We'll go through almost anything. Beta, alpha, gamma. Which one? Gamma. Which one would have? Which one would have the least penetrating? So if I held up a piece of paper, it would block it. Alpha. Remember that. Okay. All right. So now what we're going to do is take some notes on natural decay. Natural radioactive decay. So this is when elements like the discs up here just naturally decay on their own. Humans are not doing anything to create this or to alter it. And in fact, we can't control it. I can't stop these from giving off radiation. I can't speed up the radiation. I can't slow it down. Humans really don't have much control over that. That's why power plants that use nuclear fission can melt down. You've heard of 3 Mile Island, maybe. You've heard of Chernobyl. In the past, they melt down because Fukushima in Japan, because of those earthquakes. If something happens where it gets out of control and the reaction overheats, we can't stop it. Okay, nuclear reactions just happen naturally, natural radioactive. Now fission in a power plant is artificial, where we have to start it by taking a little tiny particle and slamming it into the nucleus of uranium or plutonium, but then it splits, and once that happens, we just have to wait for it to stop. So it is kind of scary and kind of dangerous, but this one is not as dangerous as fission. We'll talk about that hopefully tomorrow. But this is natural. I can't stress that enough. We're not doing anything to it. And I'm going to show you alpha, beta, and positron. So we'll do alpha decay first. So if we go to table N, let's pick one of the isotopes on table N that emit alpha radiation. So Morgan, pick one. Any of them, doesn't matter. Try and pick one with numbers that aren't so large. Francium-220 undergoes alpha decay. How does she know that? Because there's an alpha particle under decay mode. So francium-220 goes on top, because it's the mass number. The atomic number, you look over on the chart, it's 87. Now, since this is natural decay, all we do is draw an arrow. So what does this mean? It means francium is naturally on its own emitting radiation and turning into, transmutating a new particle, just like the homework. This is always kind of the same procedure. You write the isotope, arrow, blank, blank. But now we have to fill in the blanks. So we know this emits alpha, so this is going to be our alpha particle. That's why it's called alpha decay, because it gives off alpha particles. So we write 4 over 2He. How do I know that? Table up. Okay, alpha's on table up. And now we do the balancing game. So I'm going to give you 30 seconds. Fill in the blank based on the numbers there, like I did with the homework problem. See if you can do it. If you want to do it in your head because you don't want to, cross something out, then go ahead. But give it a shot. What goes in the blank? Okay, that might not have been enough time for everybody, but that was 30 seconds. I want to make sure we get enough down here today. I just added the word transmutation. You should probably do that. I just thought of it. The regents will ask one of two questions. Which of the following is natural decay? Which of the following, one of three. Which of the following is natural decay? Which of the following is natural radioactivity? Which of the following is natural transmutation? You kind of have to know they all mean the same thing. All right, so can anyone fill in the blank? Dylan, what do you got?
216.
216, very good.
Over 85.
85, very good. Who's that? I'm going to cut to the chase. AT. Astatine. AT. So, how did he do that? 2 plus 85 equals 87. 4 plus 216 equals 220. That's alpha decay. Next, beta decay. So beta decay. Marcy, pick one on table N, please, that emits beta. Carbon 14. All right, so carbon 14 over 6. Arrow. Blank plus blank. This blank is going to be a beta particle. How do I know? Because table N told me. It had B minus as the decay mode. Monique, what is the symbol or the notation for beta?
0 over -1e.
0, -1e. Go ahead, I'll give you guys a little time to figure out the blank. I know I'm going quick. Stay with me. All right, Shane, what do we got for the blank?
14.
Yep. 7, yep.
0.
What? You already gave me 2 numbers. Give me a letter. Oh. Try again. Who's atomic number 7? Who's number 7 on the chart? Periodic table. You can look over there. Who's number 7? N. There you go. That's how we do it. We look up that bottom number. So do the math, then look up the bottom number. So carbon transmutates into nitrogen. I'm going to show you a video, not today, on how carbon 14 works. I can explain it, but the video's better, I think. So we'll do that. It's kind of cool. And the last one, positron. Again, the reason these are called what they're called, in other words, alpha decay, beta decay, positron decay, is because that's the particle they emit. That's what they get rid of. And remember, they're emitting them from the nucleus, because it's nuclear chemistry. Slade, pick a positron.
CA37.
Ca37, calcium 37, atomic number 20. Notice how the atomic number never changes. It's just the mass number, right? Okay, Yield, blank plus blank. Here's our positron. 0 plus 1e, that's a positron. I'm going to go quicker here. If we fill it in correctly, this is 37. This is 19. We go over there. Number 19 is K. All right, because 19 plus 1 is 20. 37 plus 0 is 37. Always use the arrow as kind of the middle of the scales, right? That's the balancing on both sides. So that's positron decay. So that's your three forms of natural decay. Gamma, I can't show because gamma is 0 over 0. So this would be identical to that, and that's not what happens. So there's no way you're ever going to show a gamma equation. You just have to know gamma is part of this. Gamma is also a form of radiation. Okay, real quick, let me give you at least one example of artificial transmutation. So artificial transmutation or artificial radioactivity, I'm just going to leave artificial transmutation, is when scientists, physicists, chemists take isotopes and put them in labs with particle accelerators. What is that? It's a building, or you could say a machine, that speeds up tiny particles and then slams them into the nucleus. Kind of like a bowling ball into a bunch of bowling pins. They bounce around. Sort of. That's what happens. Sort of. And the bowling ball is way too big for that analogy. But the point is, you're smashing the nucleus and something new is created. So let me give an example here. Let's take, I don't know. Let's go with potassium 41 over 19. Let's hit it with a neutron. And as a result, beta is emitted. You're going to fill in the blank. So I'm going to talk while you're doing this. How is this artificial? I'm just going to put a little star here. The neutron, so that neutron right there, 1 over 0n, is, the regents will use the word bombarded into the nucleus of K41, producing beta, which is that, and a new nuclei, which is that. So this is called artificial because scientists will take this neutron, speed it up, and slam it into the potassium, forcing this thing to do something it doesn't want to. And in the process, it gives off radiation and turns into something new. That's the transmutation. So I'm just going to fill it in because the bell's going to ring. The top number is still going to be 41, but the bottom number is going to be 20, and that's Ca. So that's artificial. Hold on. Got a worksheet. Sorry. I'll take responsibility, but it's the iPad's fault. So you are filling in the blanks on this page. All the blanks, you're going to fill them in just like we did in our notes. Max, if there's extras, just run them up here, please. Have a wonderful day. I will be after school if you need some help.